Unmute. All right. So we're here starting Windows today. We've been doing nothing but Linux up until now, and it is time to start Windows. So let me bring up my slides, which are here. Good. All right. Windows is, of course, the most important target in many ways. And I have probably already said this about this class, but this class and 126 essentially cover the same content. The most important thing to learn is Windows internals. Now, we did some Linux attacks, which are fine for general information, but most of the time what you really care about is taking over Windows. And the most important thing to know about is how Windows works, because Windows is very strange and very different than Linux, and almost all the attacks involve abusing the way Windows works. So here's what we're going to talk about. The Windows API is how you do everything on Windows, and you need to know about PE files and DILs, which are a type of PE files, Windows heaps, threading, and DCOM, which is very strange, and it is the reason why Windows has so many vulnerabilities. So, all right. Everything here is Windows 32, the older version of Windows. Windows 64 is similar, but we're not covering it in this class yet. We'll have a little bit of Windows 64 stuff coming up and a little bit of ARM stuff coming up later, which is going to be what comes after Intel 64. Although, as far as I know, Windows has not yet announced the move. Mac is going to move, and servers are going to move to ARM soon, and I would imagine Windows will not be far behind. Anyway, so in Windows, we've talked about this before in general terms. The kernel is the only part of the operating system that is authorized to directly touch the hardware in Windows as well as in Linux. So if you want to do something like save a file on the disk or send a packet out the network card from an application, you can't. All you can do is ask the Windows API to please do that for me. You have to pass it through the API. And so that's the application programming interface. And this is what you mostly do in Windows. You just learn how to use the API, make API calls to do everything. An API call to open a window, API call to read the buttons and so on. Yeah.
Is there like a thing like ring layer 0, layer 2?
Well, there's ring, they call ring 0, the kernel, and ring 3 is userland. Those are the main areas you use. Rings 1 and 2 in between are never used by any modern operating system. But there is now something called ring -1, which is the hardware virtualization component, which was added after this system, which makes it possible for virtual machines to directly connect to the hardware. And this is why you could do something, you can do this, which is kind of mind-boggling. You can have a 64-bit machine, you can install a 32-bit operating system, and then you can run a 64-bit virtual machine on it.
On top of the 32?
Yes, because the virtual machine from hardware-assisted virtualization goes right to the hardware without passing through the OS in the middle, which is kind of nuts, but that's the way it is. Anyway, all right, so the Windows API is a bunch of DILs, which are libraries that are loaded that offer all these functions, and what you do in your program is just call them. And they change all the time with each version of Windows and Service Pack, but most of them stay the same in most ways. So here's the Windows API call to create a window. And when Microsoft names their APIs, they always use this pattern of using capital letters on each word and running the words together. And then when they have later versions of Windows and they have to extend it, they put an EX on the end. And there might be XXX. And sometimes they end with an A or a W to tell you whether they're using ASCII or wide words, which are Unicode. Those are ways to spot Windows API calls. And then they have a series of arguments here which specify what you're going to do with the window, like its title and whether it's going to have a scroll bar and all that sort of thing. DILs are the precompiled libraries that come with Windows, and you can see the loaded DILs with Process Explorer. If you view the lower pane, you can view lower pane, you see the DILs that have loaded that are connected to service host, and there they are. And there are a bunch of DILs loaded every time you'll boot Windows. And every new program you launch, will either connect to the existing DILs, or if necessary, it will launch additional DILs to get all the libraries it needs. And this is the main way malware takes over your machine, is by altering a DIL file or tricking your program into loading a malicious DIL file. So the fact that you can link new code at runtime makes it vulnerable to alteration at runtime, and that's what most malware exploits. This is the genius and idiocy of Windows. We're going to get that. So Windows has this shared library system, which means most of the time code loads faster and it's smaller and it uses less RAM, but it also creates a serious hole, which almost all malware exploits. So these things are portable executable files. This is the fundamental file format used by all Windows executables, EXEs and DILs. And this is just the format that specifies how Windows can load something to run it. And PEView lets you see it, which you're using quite a bit in the malware analysis class. PEView lets you see your file, and you'll see that there's an import table and an export table in most files. And here's the fundamental sections in the file. This is Notepad. It has text, data, resource, and relocation. Everything has to have a text section, which is what includes the executable code. The fundamental rule for all Windows names is everything in Windows is always named the opposite of what it really is. And so the text section does not contain readable text. It contains unreadable machine code. The actual readable text is stored in the data section. And it's how it goes. And the reason, it's not that Microsoft is nuts, although sometimes it seems that way, it's that all this stuff is really, really old. And these names come from generations of code ago when people thought about it all very differently. Anyway, so here you've got the import directory table, and you see here's the list of the DIL it's using. Advanced API 32, kernel 32, GDI, graphic display interface 32. So Notepad needs to load all these graphic libraries so it can pop up a button and say, do you want to save your file or something? It's even Notepad, which you might think is not very graphical, needs all this junk. There's user 32 to get user input, keyboard presses and such. And that in the DIL file is a format where you specify all these libraries and what functions are used so it can read that to load it. That's all portable executables have that. So what's that? This is PEView. Yeah, PEView. Yeah, free tool.
You can view any documents.
Yeah, or .exe or .dil. Yeah, it's one way to it's one simple way to open it. There's another one that's good called PEID and another one called Lord PE. We use them in the malware analysis class.
Project ASIN. Project ASIN.
I'm not sure about this class, but I know in the malware analysis class we use them right from the start. This is the first thing you do in malware is look at the portable executable file header to see what you've got. And there you can answer simple questions like what language it's written in, when it was compiled, and what libraries it uses. And that's often the first thing you do to find out what you've got and decide what tool to use next. Anyway, so you got text and data, and you may have any number of additional things like iData, resource, and relocation, but you almost always have text and data. And I saw a chat come in. Yes, section 152, chapter 15 covers these applications. Okay, fair enough. Yep, chapter 15 of 152, that could be. All right, anyway. So now the DILs have a base address, which is where they would like to load in memory. And they would be fastest to load and fastest to run if they load it at their preferred address. But you might have two DILs that have the same base address, and they cannot both load at the same address, so one has to be relocated, and that's why you have that relocation section. In order to relocate them, it has to rewrite some of the code. Now, some of the code is going to be relative jumps, which are fine, but some of it is going to have absolute hard-coded addresses. And the relocation section lists all the changes that will have to be made to the binary to make it run in another location. So it will take longer to load if you have to relocate it, but it is relocatable to that extent. This is why professionally written code, like the stuff Microsoft makes, has a different base address for every DIL. But third-party companies that are more sloppy might just use the same base that something else is using because they don't care about this relocation. All right, so I got some cahoots about that to get you started. Let me get my bar on the screen. Okay, cahoots. All right. Log in. And I'll make it so it's relatively high for the people in the classroom where the screen is too low. And my favorites are here. So we are up to 6A. All right.
Wait, are the quiz due today for chapter 6?
I think so. Yeah. Yeah, it was due before class.
Canvas was due last week.
Oh, okay. I think somebody told me. I think now the dates are fixed. But anyway, yeah, it should be in today.
Okay.
Yeah, before class. If you're still doing it, they stay up though, even when they're late. So you can still take them if you didn't. All right. And good, there we are. All right. And let me open a document to save the winners. All right. Oh, okay. All right, I'll wait a few more seconds to see. 7 might be all we get. Nope, maybe not. All right. All right, this looks like maybe enough. Apparently so. Okay, where's the precompiled library code? Okay, they are dynamic linked libraries, DILs. All right. What are the functions Microsoft provides for access to the kernel? That's the API. To be fair, the API is not always directly calling the kernel, but kernel 32 is one of the API DILs. There are other routines that are not directly calling the kernel, but they will then call something that eventually calls the kernel to do pretty much everything. What's the format for all Windows executables? E for portable executable. They are not all EXEs. Some of them are DILs, some of them are COMs, but they are all portable executables. Portable executable is the encompassing file type. And what part of it does rebasing? Okay, relocation, good. And where are the machine code instructions in your PE file? Okay, in the text section, just where you would think they would not be. All right. And where are the icons? They're in the resource section, and there is a program you can download called Resource Hacker, which is used by game hackers down through the ages. And what you do is you just change the resources, and you don't change anything about how a game goes, but you can change the pictures to have your face on the enemies or something. That's what happens if you mess with the resource file. You change the way things look. That's where the icons and where the messages are, the text messages, but it doesn't have the program control. That's in the text section. So let me put
what's that called?
Resource Hacker. It's quite useful, actually. Daily and front row. Well, you guys will tell me eventually who you are. You get points, but this will do for the moment. All right. And all right, so we've got time to go on for another section here. So, all right, so now you have imports and exports. If your executable uses a library function, the library, like kernel32.dil, has many functions, 100 or more, and you probably only need 3 or 4 of them. So those are the ones you import, specified in the header. I import these 3 functions, those are the ones I use. Exports are functions you offer to other functions. So an exe typically doesn't have any exports except one, start, which starts the program. So the operating system started. It doesn't usually offer other ways to come in. There's only one way it's intended to come in. But DILs have many exports. They have a whole bunch of functions in a big library, and other applications just want to use 1 or 2 of those. And you have many ways to enter it. So here's Notepad's imports. It uses all these other things like registry, set value, and isText Unicode, and create a window, and so on. Everything it does by calling all these API calls. And here's the list of them on the import table. Here's edbapi.dil exports. This is the advanced API, so it has things like access, check, and abort system shutdown, and add audit, and so on. So many that whole page is still in the A's. Hundreds of functions it provides to control the appearance of things on Windows. So when an exe launches, Windows loads the executable file, then it looks in the header of the PE and it says, oh, I need this library, and this library, and this library. Then it hunts for those libraries, and if it doesn't find them, it then crashes with a missing DIL error, which used to be the bane of existence on Windows 98. There is a fundamental weakness in Windows which is sort of mind-boggling. When you uninstall a program, it knows to remove the executable, but it doesn't know whether it should remove the DILs or not, because the DIL might be used by some other program and Microsoft doesn't know. So when you uninstall programs, especially back in the old days of Windows 98, they'll ask you, this program is using x473.dil, shall I remove it? And I'm like, how do I know whether you should remove it? And so nobody really knows what to do. And so your uninstalls would remove the DILs, and then other programs would break at random, and you'd cry. And Linux solved this problem, like most of these things, 25 years ago with a thing called link count. When you make a file, you have a link count on the file, which is how many other files are using it. And you watch the link count, and when the link count falls to 0, then it's safe to delete. But nobody gave Microsoft this tip, so they haven't solved this problem yet, as far as I know. Anyway, that's the game called DIL Hell of Windows, where you keep on having to reinstall DILs over and over. There are even libraries on the internet of unauthorized pirate copies of DILs to replace all the missing DILs on your Windows machines that quit working. And sometimes they have malware or something in them. Anyway, kind of madness. This is how Stuxnet worked. Our attack between the United States and Israel on Iran used a malicious DIL. So when you plugged in a USB stick, the process that drew this graphical window, you did not have to open the files. If you just opened the main folder, which often happened automatically when you plugged in USB sticks, the process that drew this graphical desktop would load this DIL off of the stick, and that DIL contained malware that would infect your machine using several zero-day exploits. And it would then use your machine to scan everything it was connected to see if it was connected to a Siemens controller, which was running an isotope separator in Iran. And if it was not, it would just live on that machine and continue to infect every USB stick that's plugged in. And if it was, it would then put malware on the USB stick. This is how the United States and Israel defeated an air gap and destroyed the uranium isotope separators in Iran, even though they were not connected to the internet. They infected all the USB sticks until they found their target and destroyed it. But the Israelis did something that caused this to leak out and become known. These operations are secret, and they try very hard to wipe all their traces. There was one called Wiper that it infected oil companies in Arabian nations and then wiped the whole hard drive, and it was done. Part of the operation is to sneak onto the machine, do the damage, and then hide all traces. No one would be able to get a sample of Wiper because it kept wiping the whole hard drive. By the time you knew you had it, there was no sample to retrieve anymore. But this did not clean up its traces well enough, and we got caught. And it eventually came out that we had done this. We have probably done many other similar campaigns that we did not get caught for. They're out there. But this is an example of official state-sponsored attacks. You don't just send an email to a million people and get caught and get put in antivirus. You make something that will very sneakily crawl around and never do anything except to the chosen target and then vanish again. That's how you can keep using stuff over and over. There's a series of news articles that came out this week for one that various governments are using to spy on journalists. And they infect their iPhones from a link, and then they live on just the particular chosen targets, and they steal all their text messages and phone calls from then on. There's a company that sells this stuff to governments, and they use it to spy on people, and it has this property of being very targeted. It doesn't just infect a lot of people, it infects only the ones you wanted to infect to avoid getting caught.
Oh, yeah. Are you going to get into more like Android?
Not in this class. This class is not going to do Android. The mobile device hacking class, which is coming up next semester or the semester after, is mainly Android.
Oh.
And Android is very vulnerable. Android is great fun to hack. It's wide open. It's the way computers were in the 90s. It's just ridiculous. It's very easy to hack Android apps, major ones, like the top banks and insurance companies. You can totally hack their apps. It's appalling. If you take that class, you'll get an iPhone. That's what I did. Anyway, so now all your executable processes think they're running at the same address, 400,000 in hex. That is their standard address. You may have noticed the way we're compiling Linux code in this course, everything thinks it's running at 0804 in Linux. It's the same thing. They have some standard address. They're not really running at 0804 in Linux, and they're not really running 400,000 in Windows, because you can run multiple applications at the same time, and they can't all be at the same address. Those are relative virtual addresses, like a virtual machine. The program's internal addresses think they're at that location, but they're really located somewhere else in memory. And on modern Windows machines, that location is random. Every time you restart them, they move randomly in memory to overcome buffer overflow attacks. So anyway, that's this is called the relative virtual address. So if you, possible physical memory address might have one process A at 300,000 and process B at 500,000, but they both think they're at 400,000. There's a mapping table up to where they really are, which they don't know inside the program or need to know. They work with the relative virtual address. Ollie debug, for example, you'll always see your code starting here at 400,000 and a little more, because it loads the way things really run. All right. There are a lot of heaps. When you need to store data temporarily in C code, you use malloc to allocate some space, and then when you're done with it, you free it with free, so that space can be reused. And this is done a lot to make programs consume less RAM. Linux has one heap, but Windows has many heaps. Windows heaps are quite complicated. You can do heap overflows and heap corruption attacks on Windows, but they are pretty confusing, and Microsoft has very good heap defenses, especially in the latest version, because of the blue hat contest. In the early days, like Windows 95, 98, and Windows XP before Service Pack 2, until 2002, Microsoft had an official policy that security is a waste of time, just don't even bother. The only point of the correct level of security for our products is to make a product so that a legitimate user trying to do a reasonable thing finds that it works. You do not need to worry about malicious users carefully crafting attacks, because that's just too much work and not worth the bother. In 2002, they reversed course on this. But anyway, they still continued to have a public face where they said all the hackers that develop attacks should just shut up and not tell anybody, and then everything will be fine. But of course, that didn't work, because there are smart people on the bad side too. So if I find something, probably somebody in Russia finds it too, and if I shut up, that doesn't really fix the problem. So Microsoft gradually became less and less hostile towards ethical hacking, until starting about 5 years ago, they finally embraced the ethical hacking community. They brought us all beer at TorCon, and then they started the Blue Hat Contest, where they will bring you to their convention by invitation, and they will invite you to hack their stuff and fix it. And they will pay you $100,000 if you hack the latest version of Windows, and they will pay you another $100,000 if you build the defense. So the defenses are typically written by the ethical hackers that develop the attacks, and Windows heap defenses are getting very good. In the latest version of Windows, every version, they have a bunch more heap mitigations that break all the previous heap exploits. So, you know, they're accepting the ethical hacking community is making their product much better. Anyway, didn't Stuxnet inadvertently spread through the net? Yes, I think it did. Windows DILs can be written in C, and I think other languages, most commonly C++. Is what I see most often. They're good questions. Anyway, so threading. There's a fundamental problem with all computing because of the hardware, which is heat dissipation. Long ago, chips kept getting faster, about twice as fast every decade or so. And then around 3 gigahertz, chips stopped getting faster because they will burn up. So they were not able to make the core any faster than that. So what they did was make multi-core processors with 4 or 8 or 16 cores on the die. And that means in principle, you can get more processes per second, but in practice, most code can't use it because most code has an order. Do step 1, do step 2, do step 3. Even if I have 4 processors, I can't do step 3 until it has done step 2. So in order to get more benefit of these multi-core processors, they try to use this threading system where they break your code up into independent threads that can move forward independently. So one thread can go forward while the other thread is waiting for something to happen. That's the plan here. So you can see them in Task Manager. If you load Task Manager in Windows, you'll see that I have 41 processes, but 677 threads. So each process has 10 or 15 threads, and each thread has many handles. The handles are the named objects, like pointers to a file, pointers to a process, and mutexes, which we talked about in the other class. Mutexes are pointers in the RAM that multiple processes can see. So one process can send a signal to another process. Anyway, and threads are what actually gets CPU time. The processor strobes gives this thread some cycle, give this thread some cycle, give this thread some cycles. It's strobing around among them so that everybody gets a chance to move forward. All right. And you can see them in, you can go into Process Explorer and you can see each thread and you can see all the handles in the thread here if you want to. You can see all the threads, you can even see the handles on each thread. And typically you don't have any reason to dig this deeply into things, but you might want to debug a driver problem or perhaps to find one interesting fact about a piece of malware. All right, so I got some more Kahoots about that stuff. Get rid of this one. And we are up to 6B, which is here. Okay. We only had 8 or 9 last time.
I guess people are watching VODs.
VOG?
VODs, video on demand.
Oh, that could be, yes. Yeah. Yeah. I mean, I don't know what they're all doing, but anyway. I'll wait another few seconds to see if anyone else is coming. Are you trying to connect there?
Well, I don't have a signal, but I didn't.
You don't have a signal? You should be able to get on the Wi-Fi.
Yeah, no, I can get on the Wi-Fi. I just haven't yet.
Oh, okay. Well, give it a shot. You can go to danger zone if you like. That won't give you any login or anything. That's why we put it up. Aha.
Okay.
Yeah. The SSID is the same as the password. And it puts you outside the City College firewall, which probably doesn't really matter if you're a phone, but it matters for a lot of what we do here. How's it going? Did you get on?
Don't worry about me.
Okay, fair enough. I'll start with this then. Off we go. Okay, so. Okay, so what part of it?
Can you hang on 30 seconds?
All right, those are the exports. The DIL export stuff, so other programs can import it and use it. And let me kill the voices so these people don't irritate each other. All right. So, okay, what memory section is single in Linux but multiple in Windows? That's the heap. All right. Which one of these has the largest number of instances on a Windows machine? All right, handles. You have Windows, and then you have processes, some with Windows and some without Windows, and each process has many thread, and each thread has many handles. The handle is the most numerous item. And what part of this is used to allocate CPU time? Okay, the threads are the units of allocation. All right. So daily is run twice, and so does front row, and I have ashed. All right. And I think we can still just keep going here. So, all right, and now we get down to DCOM, Distributed Common Object Model, which is how Windows got to the bizarre place where they are. And this is related to remote procedure calls. Here's the idea. Microsoft has always been explicitly commercial. Back in the really early days, there were other people that wanted to make software free and everything. And Bill Gates, right from the very start, right from his teenage years, said, I'm going to copyright stuff. People shouldn't make unauthorized copy. I'm trying to make a business. We're here to make money. So the purpose of Windows is to be a platform to make it easy for people to write code and sell the code. So there should be a thriving marketplace, and you should be able to buy other people's code and use it. Therefore, you should be able to reuse your code. So you could write something, some useful package, and you could sell it to other software developers who would then pay for your licensed library and build it into their product. Microsoft intended that right from the beginning. So this is how it works. You would write a COM object. You could write it in any of a variety of languages like C++ or other languages. Then it would interoperate with anyone else, and it would come with an interface description language that would say, here are the inputs to my routine. And then you could sell this to anybody that wants to buy it, and they could just plug it into their app instead of having to write their own. And the DCOM looks like this. You define the data coming in and whether it's strings or long or what it is, and how big it should be and what order it should be in. And then people that obey those specifications can use your code. That's the idea. Now the problem. This also works with these UUIDs, also called GUIDs, that are 128 bits long. You'll see these long numbers. Those are the identifiers for these DCOM objects. So now you can load a COM object two ways. You can load it in a process space as a DIL, and then it will be available only to that one process. Or you can launch as a service by services.exe. Now here's where you begin to get into security nightmare. If you launch it as a service, it is now available to every process on the machine, and it typically launches before the first user logs in, so it typically runs with system privileges, which is the most powerful account, more powerful than the administrator, because it runs before anybody has logged in, so it can't use any other identity. So now it runs as a service. This means it will now be 1,000 times slower to call, because it has to go through a lot of overhead to find the service that's shared by many things. So what happens, you see them in the Service Control Manager here. In Task Manager, there's a list of services. These are all the services that are launched, and notice how some of them run as system. That's because they launched before any user logged in to make a service available to all users, and a lot of the Windows does run that way. Okay, so Microsoft's plan is to make this easy. So what happens is you can take a program. So here's what happens. Somebody writes a program, and they write a library to be used on that one program loaded in its memory space. Then the people who market it can take that and make it into a service and make it available to every program on the machine, and the original developer does not know this happened. They probably quit years ago. Then they can make it available over the network to everybody on the internet. The same code that was originally written for a very limited purpose in a different environment. This is what happened to the internet. Things like Telnet have been around. The original purpose of Telnet was to take a terminal and connect to a computer in the same room through a cable. That's all it was supposed to do. You type a letter, that one letter goes down the cable over to here. Then the internet appeared. People ported it to Telnet. So now you take those unencrypted characters and you send them over the internet, which is fantastically unsafe, but people didn't think about that. It worked. And they continue to use Telnet on the internet, which is insane. And here's what happens. You end up with this stuff that was originally intended for a limited environment, and you end up exposing it to the whole world when the original code was never written with that in mind. This is very much like what happens when you go to the cloud. The cloud is so great. I'm trying to move my stuff to the cloud, so is everybody else. But what people typically do is they go to their existing servers in their data center, and they make an image of that, and then they push it up to Amazon, and they don't realize that now it's exposed to the whole world. And before, it was behind their firewall and their switching, their routing. And that's why we have a huge problem with Amazon open buckets. People take data from their stuff and put it in the cloud without realizing that the cloud makes it much more available. And that's why some people get very upset about this, but you can take code written for one process and then sell it to the whole world and put it on the internet and let everybody share it. And that would be great, except for the security consequences, which turned out to be not so great. So you can see the RPC endpoint mapper, the remote procedure call in Microsoft lets you access all these available processes. And so you send queries to this TCP port 135, and it will then do a request via UUID, this long UUID, finding out what you've got. It'll give you a list of all the services that machine has. Many, many services are running on port 135, and this is why you will hear an unending chain of Microsoft malware that attacks you through port 135. This is why it is such a security nightmare, because 135 gives you connection to all those things which have been made available to the network, which were probably never intended for that purpose. Things that have been recycled and reused to put on the global stage when they were originally written to live just in one little application.
Wait, so I just said like the get request for 135.
Yeah, there's a protocol. You send a request, it sends you a directory, then you can interact with each component. But it turns out that many, many installed applications put unsafe things on here. And that's why so many worms go through here. So many, many components depend on RPC. A lot of things do. If you double clock remote procedure call, you'll see all these things. DCOM and RPC are required by all these things. It's just the A's and the B's, the things that do backups. That's why it came up today in the earlier class. We were firewalling off machines, and people said, what ports do you have to leave open? And I said, well, on Linux, you might leave just 22 and 80 open, but on Windows, you have to leave about 12 ports open on the domain controller. All this stuff has to be available, or your domain will not work right. And RPC is one of them. So that's the point. You have code written in a limited environment, which is then deployed on the world stage, often by people who really don't understand how it works very well and are unaware of the fact that it's not secure enough for that environment. So there's a bunch of exploitation tools. You can do fuzz, spike, and other tools can fuzz and find vulnerabilities in RPC, and there are usually a ton of them. It's probably one of the major insecure services from Microsoft. Now, there are other strange things about the Microsoft operating system. Remember, we just looked in Task Manager, and we saw that some things are running as system, other things are running as SAM, and so on. How does it know who's running the process? Well, it turns out it knows because of a token. The token is this 32-byte integer, these tokens here. It is the handle that it is a data structure that determines who is using the process. And it turns out the token is just sitting there in memory, and you can just steal it and copy it and start a process by somebody else's token. You can do it with Metasploit. We do it in 124. So you can create a thread and you can copy an available token to it. So if your network administrator, your domain administrator runs some kind of process like a backup or an update, and they leave a process running on a workstation with domain administrator credentials, anybody that puts malware on that workstation can steal that token and run more processes with domain administrator credentials. This is one of the many consequences of this system, closely related to the pass-to-hash attack, which Microsoft has finally attempted to mitigate with silos. From Server 2012 R2 onward, there is an optional feature in domains you can turn on which specify that certain highly privileged accounts can only log into certain places and nowhere else. And the idea is you can make it so your domain administrator credentials can only be used on the domain controller, and they cannot be used on a workstation that connects to the internet. So that if the domain administrator is at a workstation and they want to do something on a domain controller, they have to right-click Run As and type in the domain administrator's password, which goes over the network to the domain controller, but there is no token generated on the workstation with domain administrator privileges, so that the malware on the workstation doesn't get a chance to steal it, because this is the main way you take over Windows networks now. It has been for 20 years. You just find domain administrator hashed passwords and other tokens just floating around out on the unprivileged workstations, where you can just trick someone into clicking on an email attachment and putting malware on it. And then you find the domain admin credentials just sitting out there in that unsafe environment. That's a very common situation. All right, and then there's exception handling. In Windows, there's a thing called the structured exception handler. If you have some kind of error in your code, like it attempts to execute an illegal instruction, for example, it attempts to access memory outside the range of memory allocated to that process, or it attempts to do a kernel code and it is not running in kernel mode, or it tries to divide by 0, there's a whole series of things that are errors. So if one of these things happens, then it raises an exception. The exception goes to, first, it tries to see if your program provided an exception handler. If you are a careful coder, you will not want to lose control. So you will say, if something happens, I will write an exception handler that will take care of it. This error will now pop up a box within my code or something. So the first thing it does is look if the original programmer wrote an exception to handle this. And then it will try to handle it there. If that fails, it will then pass the exception to the operating system, who will then pop up a generic message, this program has crashed, would you like to run the Dr. Watson debugger or MinDebug debugger if you have one installed? And if it's in a kernel routine, the operating system cannot pop up a box or anything, then you see the blue screen of death if the kernel routine crashes. Anyway, that's the game here. You can have custom exception handlers if you're a careful programmer, but if your exception handlers don't do it, it will pass to the operating system. You can see it in Immunity Debugger and Anley, which is the same thing. You'll just see a series of pointers here. These are pointers which point to code, and what happens when you have the exception is it calls this routine to see if it wants to handle it, and if it doesn't, then it calls this one, and when it all fails, then it goes off to the operating system, say we have an unhandled exception, you deal with it, and the operating system will pop up some kind of generic box or just crash with the blue screen of death, depending on whether it can handle it. So you can exploit the exception handler. If you have the ability to overrun something and you're able to change the exception handler, which is what happens with buffer overruns in Windows frequently, then you can change these pointers to point to code you want to execute and then cause an exception. And it will try to handle it there, and that's one way to get control of the machine. All right. So in order to do this stuff, you need a debugger. There are a lot of debuggers. Soft Ice is an old one. People used to like it, but it's out of date now. WinDebug is the most powerful, strongest debugger for Windows. It is very unpleasant to look at. It is a command line product stuck in a very simple GUI just to make it pretend not to be a command line product. And it's what Microsoft uses internally. And it can debug both the kernel and user land. So experienced pros use WinDebug, but at first, WinDebug is very hostile to use, sort of like GDB on Linux. Ollie is very popular with games. People cheat at games and everything else. It's been the hacker's friend for decades, but it's been out. It has not been updated much. Immunity is probably the best. Immunity bought the Ollie code and kept maintaining it. So Immunity is probably the most. Immunity is essentially identical to Ollie. One thing to know about Ollie is they updated it from 1.1 to 2, and in 2 they broke everything. 2 will just lie to you, tell you. They're all free. Yeah. Yeah, but anyway, but Ollie Debug 2 is useless. It will actually give you false statements about the code. It's amazing that they even released it. So if you're going to use Ollie, use 1.10, which is very old, but it still works fine, or use Immunity, which is currently maintained and updated. Anyway, so here's what the debugger looks like. Immunity or Ollie, they both look the same. They're both essentially identical. Immunity is probably the right thing to use these days. I should really get Ollie out of all my projects. You get 4 panes. When you launch a Windows process in a debugger, it prepares it. It loads all the libraries and gets it ready to go, and then it pauses. First thing you do is look in the lower right and see that it's paused. When you first load a Windows program, it is not running. It is waiting, because presumably you ran it in a debugger because you want to look at it or change something. So it pauses. If you want to actually run it and interact with it, you have to hit this button up here, the right where there will be arrow, to start it running. When it pauses, you see the assembly code here, which is ready to execute. You see the registers over here, just like you know from GDB, EAX, and EIP, and ESI, and EDI, and all that jazz. And down here you have the stack. The stack is nicely presented. with a series of words. Here's the 32-bit words on the stack, just counting up 5C, 60, 64, 68, 16, counting up 4 bytes at a time. The raw data is stored here, and if that pointer points to something, it shows you what it's pointing to. This is return to a library. This is just junk. This one is a pointer to something. If it points to a string, it'll show you the first few letters of the string here, so you see what it is. So tries to make it easy as possible to understand your stack. Notice these green arrows, green brackets in the stack. This shows you stack frames. When you call a routine, the first thing it does in the preamble is it loads enough code to set aside enough room on the stack for the local variables. And then while it's in that routine, it uses just that much stack. And when you call, the calling routine is up here with another stack frame stacked up on the stack. And your lib marked there to help you do that. So what we've done in the Stack Overflows on Linux is we found variables like here that we could overrun, put a until we hit the stored return value, which would take over the machine. And here you have a graphical presentation of it. And on the left, you have a hex dump pane. You can just dump any part of memory you want to in raw hex there, just so you can see the hex and the ASCII for anything of interest. So I think that's it for this stuff. I got some more Kahoots, and then I'll show you the first Ollie project, which I realized looking at it this morning is duplicate pretty much of one that you've seen if you've taken my 126 class. So some of you will find it very easy, but if you've never used a debugger, it's a good place to start. We're just going to modify putty. So.
Wait, but after you modify, like, this is detect by
It's a very good question. When you modify code, doesn't your antivirus warn you? And the answer is no, for no good reason. If it was F-Secure, it would warn you. F-Secure only takes code from known good sources and warns you if it's modified. You'll see, for some ungodly reason, Windows lets you modify it and run it. It even has a signature, this code, and Microsoft Windows even detects that you broke the signature and it doesn't tell you. Microsoft does a lot of weird things like this. They have a security feature, but it doesn't actually save you. This happens over and over and over. It's like there's somebody in Microsoft team says we have to have a security feature, and somebody in marketing or management takes all the teeth out of it before the product ships, probably because it broke something. But it's just amazing how often they say, we have this new thing, boy, that sounds great. And when it comes out, it's actually no good at all. You always seem to get only... Yeah, the signature act computes the hash, and some signatures even call back to the product developer. It actually has a key which can verify on the internet, like an HTTPS certificate, so it knows it really was signed by that company, and it's proven to be that company. And that's what Microsoft likes. They say you only run code that is signed by somebody you can trust, like Oracle or something, and you know it's really genuine Oracle code, because they think in terms of like lawsuits and warranties and stuff. That you trust a huge company, you would sue them. That's why you're supposed to have code signing certificates and signed code. But strangely enough, you can have signatures which are broken and it doesn't even tell you. You can also, another thing is, you remember all those sections of the PE file? I went to a hacking conference a few years ago and they had modifying signed Windows executable. And I said, how is that possible? He said, it's easy. It only signs like 2 of those segments. You can just put code in the other segments and it doesn't detect that. You get used to this with Microsoft. It always sounds good until you look at the details. And then you find that they made a shiny new lock and they only put it on the front door and left the back door hanging open. They always do this. And of course, they're not completely stupid because it breaks the current generation of malware that is using that front door. So it's not like it did no good at all. Now everybody has to update their malware. That's all you ever get, is you have to update your malware. Then they patch that, then you have to update your malware again. It never stops. Anyway, let's look at these. So where do you find the inputs and outputs of an object? The IDL file, interface descriptor language file, goes on a DCOM object to specify what should be given it to it. Where's 128-bit value? Okay, that is the UUID. By the way, Here's another fine example of GUID. You hear of a lot in Microsoft. The GUID, there's one for the control panel, and a few years ago there's this thing called God mode that came out. The GUID stands for Globally Unique Identifier, and it is the same on every Windows machine, so it's not global at all. Just the general rule to remember all this is every time Microsoft names something, the name is always the opposite of what it is. Anyway, so if you divide by 0, what do you do now? Okay, you use the exception handler, the SEH. All right, which one of these listens on port 135? That's remote procedure call, endpoint mapper. Which one is 32 bits? Tokens 32 bits, that's what it says. I wonder if it's really a token or a pointer to a data structure, but I think it might just be the token. Anyway, and which debugger can debug the kernel? Okay, that's WinDebug. I don't think we'll be using it in this class. We're using it in the malware analysis class. But I don't think we're doing kernel exploits in this class yet. All right. Which debugger had a good old version and a bad new version? Ollie Debug. By the way, Microsoft just did this too. They just recalled the patch they put on in Patch Tuesday last week. It was deleting people's files, so they had an emergency recall of the patch. This is, I think, the 4th time in the last 12 months that Microsoft has had to recall their patches. I talked to a Microsoft developer about this a year and a half ago, and I said, dude, you're making people mandatory take patches? That isn't a good idea because your patch quality is too low. And he said, yeah, I know, that's what I said, but they didn't listen to me. You can't turn off the updates in Windows 10, and the updates are poison. This is pretty rude. Anyway.
Wait, can you turn your networking like metered?
Yes, you can put your networking metered mode,
Right.
and Kirk found a way too. You can disable a certain service and that will do it, but they don't give you any easy way to do it. It's not in the GUI. You can't just go into like update in control panel and turn it off like you should be able to if they're gonna be so rotten. Because Microsoft is determined to ram them down your throat. But if they're gonna do that, they should have more quality control on them. That's my opinion, but what do I matter? Anyway. All right, so all right, so I got Hammer Unix. I know that's his actual name in the system. And front row is 1 3 times, which is very good. It's good to sit in the front row. And Chris. All right. So I'm going to demonstrate the Ollie project. I think I'll take a 10-minute break first to let people stretch your legs, and you can tell me. I'll pause the recording for 10 minutes, and if somebody wants to tell me who, all right. And the question about port 135 is quite correct. So you have, if you have a function written originally to be in one application, and then you load it as a service, it's now available to every machine on the box, every process on that box. And if you then connect it to the RPC endpoint mapper, everyone on your network can access it. And typically, because it's so unsafe, most companies do not let this traffic pass their firewall, so it's not available to everyone on the LAN. But if you look at Rapid7, they have scanned the whole internet, and they have found there are many machines that in fact have port 135 open to the internet. And they are typically infected with all kinds of malware. And you can connect to port 135 to run a task list to see the malware they're infected with, and Rapid7 publishes that. They can see what malware they're infected with by doing this. It is not good. You should never let 135 or 445 go out your corporate firewall because they're too dangerous to expose to the world at large. However, people do. People also use Telnet and FTP and a lot of foolish things that they should never be using. Anyway, so let's take a look at the next project, which is the introduction to using these debuggers. So it's just some simple hacking with Ollie. So I've got my Windows 8 machine here, and I've got Putty, and I made a copy of Putty called Putty 2 because I'm going to mess with Putty. Putty is just the Windows SSH client, which supposedly this stuff is going the way of the dodo bird one of these days, as Microsoft puts it in by default. Looks like it's not running. So when you copy a file on Windows, it often fails to run because it locks it. The file came from another computer and might be blocked, so I can unblock it here. That's a fairly common security feature. So now it'll run. So when I run, it will connect me to a server. So if I put in the name of the server, like ad.samsclass.info, and connect, I have to shrink it down to connect. Where's my mouse? My mouse is gone. Here, mouse, there we go. Okay, I open and it says login as. Now I could type in a name and password and connect to my server. This is, however, all the functionality I care about right now. It connects and prints out that message. I would like to mess with that message. However, the question has come up before, and it's a very good question. Let's check the signature of this code. This code is signed code. If you go to the properties, it has a digital signature tab, and it's signed by somebody called Simon Tatum. And if you go to the details, the signature is okay. So this right now is an unmodified good copy of PuTTY. And the whole point of code signing is you can tell if somebody has been altering the code. So let's alter the code. Load up Immunity and load that code, which is in my downloads folder, or make it my documents folder, actually. Let's see. Documents, PuTTY 2, there it is. I can load that stuff, there it is now. The picture is pretty small and hard to see, and I think Immunity has a good solution for this. I think I can go options, view, options, appearance. Yeah, I think in Immunity, I think I was actually able to fix this and have it stay fixed. In Anley, it was actually pretty painful. So here I can go to, I've got terminal 6. Let's see if I can color scheme. Well, fonts, here we are, fonts, there we are. Now I can change something. And let's try making it bigger. There we are. This is what works in Immunity that doesn't work with a damn in Anley. You can make the font bigger and have it work. So this is the only reason I know to update from Anley to Immunity, but it's a pretty good reason. Anyway, now I move these borders up if I could. Here, border. Okay, that border. Okay, now I can point to things that are kind of big enough to see. This is the executable instructions, like push and call and move. That's the registers like EAX and the extended instruction pointer down at the bottom. Notice that the instruction pointer right now points to inside the PuTTY 2 module, and it's 400,000 and some. You can see that when it is able to figure out something about what you're doing, it puts useful hints here in color. This is a Microsoft API call, get version XA. You can spot it because the capital letters on each word, the EX at the end is common and the capital A at the end is common, indicating it works on ASCII. So if it calls a recognizable Windows API call, Immunity shows you the name of it right there to make it easier for you to understand what's going on. And this is paused. You see it in the bottom right. The program is not running right now, so there is no window for me to look at here. So now, if I want to find the code that prints that message, I can right-click here and search for all referenced text strings. This is better than just strings, the strings command on Linux or the bin text command, because it's not looking just for strings, it's the ones that are actually used in the code. And now I can scroll to the top of this. Let me try and make my window there fit on the screen better. I scroll to, I think I can make this bigger too. I hope this would also get my font changed, but it didn't seem to. So I can go to there, that's a little bit better. Anyway, I can go to the top of this thing and now I can search, right click, search for text, and I'm going to search for login as. And when I do, it finds it here. Now this is, let me zoom in on it. Okay, this is the location where it finds a use of the string 467C7C prints the string login as. So I can put a breakpoint here with F2. That turns this red. That means when it hits that instruction, it will stop and come back to me, just like our breakpoints in GDB. And the reason I did that is because we're going to see there's another one. There's this one here at 46417053. And if I search again, search next, I find another login as down here at 41CB6E. So there are two places where that string is used, and I do not know which one of these instructions actually causes my the message to appear on the screen. And if I search for next, there is no more, so there are only two. Now I put breakpoints in there, so now I'm going to run the program until I get to that instruction, and then I'll know which part of it did it. So I launch the program, it runs, it opens up another window here, running PuTTY. So in that window, I have to answer this question to proceed, give it the name of a server. Okay, so I give it a server and click open, and now it proceeds and it hits my breakpoint. So it hit this breakpoint at 41CB6E. That's we're about to print this message, and notice how helpful it is. It tells me I'm about to call something, and it recognizes that this argument of this address, let me make this a little bigger in that pane so we can see it. Well, I don't know, all right, because I changed my font, it's actually hiding some of the bytes of the raw code, but the push here as a push, and this is the address. You can see the 7C part of it. The whole address is there. So it notices that that address points to some readable text, and it shows you right here it's readable text. So this is pushing a pointer to that text on the string, and then it's going to call this function, which must eventually call print. That's how you do it. You push arguments, and then you call the function, which will print. So this is about to print that message. So now I have found it. I'm going to remove the breakpoint, which you can do with F2. That will take it away from here, so it won't keep breaking there. And I can right-click, assemble. I can modify the code here. Right now, the code is push 467C7C. And before I do that, I'm going to examine it down here in the dump area. If you right-click, I can send that to the dump. Just a minute. There, follow in dump. And I can follow the selection, immediate constant, or implicit stack address. What I want to follow is the immediate constant, which is the explicit address referred to by this instruction, which is that number, 467C7C. If I do that, now it shows me that area here, and here it is, login as. I might be able to make this pane a little wider. Yeah, good. Make that one a little wider, and make this one a little wider to match my. There. So you can see this is where login as is stored. Here's the message, login as space null terminator. So it'll end here. So that's where it goes. Now, if I want to change the message, there are two ways to do it. I could just change the data here, or I could change the address up there. I'm going to start by changing the address. So I right-click here and assemble, and I'm going to change it from 467C7C to 7D. When I do that, I hit assemble. Now it's going to offer to change the next instruction to, and I'm going to cancel it because I don't want to do it. And what it has done is changed the last byte here to 7D, and now this is login as, because it points one byte further on. And since you don't specify the length of a string in C, you go by the null terminator. The string is still valid, and it's one character short. Now just login as. That's my code. Now, when you change things in Immunity or Ollie, one thing that is very frustrating is saving your changes. For like years, I just would find it here and then change it in HXD because I couldn't figure out how to save things. Here's how it works. You right-click in the area you change. Remember, there are different memory segments. Like this is the data section and this is the text section. I just changed the text section only. So I right-click in that pane and then I copy to executable. Here it says all modifications. It is lying. What it means is all modifications to that section, which is not displayed on the screen. So for a long time, I would change stuff here, change it there, save it, and the changes wouldn't be there. So I save it someplace. I'm going to copy all to executable file. It's going to open a window with PuTTY 2, and now I can right-click and save this. I'm going to call that PuTTY 3. This is why, by the way, before I start, I always make a copy, because another thing that's very easy to do is accidentally save it on top of your original and ruin it. So now I made one change and I saved it, which is what I highly recommend. Make one change and save it, because when you make two changes, you often make them in different segments, and it does not save them both, which is very, very annoying, especially when you're new to this and the assembly is confusing enough anyway. The last thing you need is your tools not working on top of everything else. So now I made something called PuTTY 3. And so there it is, glorious PuTTY 3. let's, I'm going to close immunity, I think, because it's freezing up my GUI. Okay. Called run putty 3. Now I want to give it the name of a server. If I spelled it correctly, it'll connect. And there we are, it prints login as instead of login as. So I've now changed 1 byte, which has had a measurable effect on the code, and therefore it's broken. Notice how it didn't give me any trouble at all about doing this, but if I go to properties and go to digital signature and run the details, it'll tell me the signature is not valid. So it's signed code, and the Microsoft operating system knows I just broke it, and it doesn't do anything. I don't know what doesn't. It doesn't even at least turn on that defense it had before. This came from the internet. You shouldn't run it. Well, you know, I would think an invalid signature would be an even stronger indication that you shouldn't run it, but that's not what it does. So anyway, so now I've made a modified version of this file. I'm going to modify it again. I'll just make another copy.
But if you complete the hash, that would be different.
It would be different, absolutely. The hash is different. That's what signature doing. The hash is different, and it knows it's wrong, but it doesn't pop up a warning box or anything, which is pretty rude. So now I'm going to have putty 4, and here, if I'm going to modify it again in immunity, I'm going to change that message even more. So open putty 4, which is my latest copy. And now I can go to that address, right-click, go to expression, and I think I might have this memorized by now. I've done this one so often. B6, no, I forget. Let me look at my instructions. It is here, 41CB6E. Okay, 41CB6E, because I'm not going to bother with my breakpoints again. I know where to go. There is the push, which now pushes 7C7D, which is ASCII login as. Notice how when I stopped and restarted it, it finally restructured these sizes so you can see the code. Anyway, so down there it is. I'm going to follow that in dump, which is follow in dump immediate constant. Here's that text. Now I'm going to modify this text. Now I think you just highlight it here and then right click binary edit. Yeah, now I can change that code. And I can type binary down there. I think I can type ASCII up here, which is nice. So I'm going to make it darkness there instead of login as. The same number of bytes, but the same null terminator. Because if I make something too big, I'll start ending strings and making strings run into others. As you know, eventually I could have basically a buffer overflow kind of situation here where I start changing things that are going to break the flow of the code. Now I've changed that word to darkness. Now I'm going to save it here. I don't click up here. I have to click down here to save it because that was not in the text section. That was in the data segment. By the way, parenthetically, you can see the memory segments here with view memory. This shows you all the memory. And down here you see here's putty text, rdata, data, and resource, and where they're loaded in memory and how big they are. And before I changed this text section that contained the code, now I'm changing, I think, the data section. We can tell from the address, 47B1000 would be the data section. And I'm at 467C7D. So let's see where I am. 467C is here in the data section. It goes from 467B for the next 6,000. So 7C and 7D are included in the data section. That's what I'm doing. I'm changing data section this time. So I want to close this little window and maximize the CPU to make this look familiar. I right click in the area I changed, and now I copy to executable file. Thought I would have to save all thing. Nope. See what I did? I just got the data segment only, which I could save as a file. And that might be fun, but that's not what I'm trying to do. I'm trying to get into the runnable program, so I'm not going to save this. I'm going to try again, right click, copy to executable file. All right, I'm losing my mind. This is what happened to me a lot. I get confused by putty. There is some way to save it, and I am not seeing it. Let me see if my instructions tell me how to do it. I thought I did this in this project. Yeah, there we are. So I changed this to something. Now, in the lower left pane, right-click, copy to executable. Okay, they're going to tell me that was okay, which I'm not so sure. Okay, I guess it was. I thought it was not working. Oh, I see what happened. In case other people are easily confused like me, let me explain what just happened to me here. If I can get that window back to the front again. Window, there. Okay, I'm going to try and make this window bigger. This fooled me. I thought I was only getting that section, but the scroll bar is way down here. This is the whole file scrolled to the change. The reason I didn't want to save it is because I know executables have to start with MZ. All Windows executables start with MZ, and you always have this stuff here. This program cannot run in DOS mode. When I don't see that, I'm not happy. I'm not saving a real executable it's going to run. But now I see that it is there. So it is save file, and I'm going to call that putty5 and save it. And then I'm going to leave immunity. And now I should have putty5. And when I connect ad.sams class.info, I spelled it wrong. Okay. ad.sams class.info. Okay. And my mouse is not moving. Okay, there we are. Open. There, and now it prints darkness. Okay, that was my goal. And I don't know how far I went in this project. In some of these classes, we actually generate malware and put Trojans in there, so you take remote control of the machine, because you can totally modify this to do any damn thing you want. It doesn't care about the, and I think that's in the, I didn't do that in this one. I think it's probably an extra credit project in this class, because this would be the right class for that. Yeah, 8B. 8B is where you're going to do that. In 8B, you make malware with Metasploit, put it in there, and run it in a new section. Because you can easily create a new section and put it in. So I don't think I'll go through it live, but it's the same principle. You can totally Trojan code. And this is what happens when you download stuff from BitTorrent or DILS or pirate stuff. People just put up stuff with unauthorized content in it. And this is how you do it. And code signing would prevent it. There are code-signed malware out there where they either bribe or steal real code signing certificates from companies and sign malware to bypass code signing protections, but that's expensive and rare. Most people do it this way, and code signing will stop it. Anyway, that's to give you an introduction to how to use immunity, and then we're going to go and exploit vulnerable server and start developing Windows exploits in the same spirit of what we've done before, making new exploits. See, can I send a new password to my CCSF email? Dale, I think we talked about this. Just come talk to me in class. I can't control those passwords, but I can send you an invitation. You may have to make another account. Just talk to me in class. We should do it together. It's the only way to get this straightened out, I think. Okay, good. All right. And I think I'm going to end it. Unless anybody has any questions. All right, I'm going to stop the share, and then I'm going to clean up and go upstairs and help anybody that wants to work in the lab.
Like a project?
Yeah, or whatever. Something else if you want to.